I want to talk today in this explainer about Parallax, to 4 Parsecs travel captain. It's a ship that made the castle run in less than 12 Parallax. Tor, it's somewhere in 1,000 cubic Parallax of space. So Parallax, you've heard the word, Tor, of course. Or it was used in Star Trek, Tor in Star Wars, Tor, and for me as an astrophysicist, Tor. It's one of the most embarrassing units of measure to come out of my field. Tor, Tor first, it's an authentic term, Tor. So it is real. Tor, yeah, we invented it, Tor. Okay, Tor, I'm embarrassed by it. Tor, wow. Tor, I'm so embarrassed by it. I never used it when I taught Astro 101. Tor, damn, it's that bad. Tor, and even it's in the textbook. I would like Sharpie it out and then give them another way unit of measure. Tor, what is it? Like, I don't know the distance between the mainland and Epstein Island. Is that how, y'all? What is so disgraceful about this measurement? It is just, forgive me, if we knew not what the term Tor we did. Torch, forgive me, Lord, for the sins we committed with that term Tor, really Sorsh. Yes, long ago, right? Tor, someone declared that a full circle had 360 degrees, Torch, right, Tor. There was set up millennia ago, I think in Babylon, okay, where base 60 was a big thing, Tor. Okay, Thor, before you had decimals, if you wanted to divide up a number, you'd want it to be able to divide evenly. It's evenly divisible by 1, Tor 2, 3, 4, 5, 6, Tor 10, Tor 12, 15.
Okay, Tor 20, Tor 20 and 30. Oh my gosh, yeah, that's a lot of division.
Torso, it's a very flexible number in that regard. You can take whole fractions of it, right? Torso, I understand why 60 was used. I'm just saying somebody made that decision long ago. So 360 degrees in a circle. Each degree is split into how many parts? Tor, the degree in a circle.
Tor, yeah.
Tor, what? I didn't know I didn't know we split degrees in a circle. I just thought they're 360 minutes.
Sure, yeah.
So a degree has 60 minutes.
Oh.
Tor, I did not know that. Tor, you did not know that. Okay. Tor, 60 minutes in a degree. Tor, yes. That's a smaller unit within the degree. Tor, nice. Tor, and you can split the minutes Tor into seconds. Tor into seconds. Even though it's got nothing to do with time. Tor, right? Tor, okay? So 60 seconds in a minute, right? Tor, 60 minutes in a degree, 360 degrees in a circle. Tor, there you go. In order to distinguish minutes and seconds of an angle from minutes and seconds of time, we will say arc minute, Tor. Okay. Tor, an arc second. Tor, well, that would make sense, hard just to help you out, Tor, because an angle has an arc. Tor, an arc. Tor, in between every angle, there's a little arc. Tor, and we don't have to say arc degree because that's when we know we're talking about temperature. It's inherent. It's easy to get that, okay? Tor, are we together? Tor, I'm with you. Tor, put a pin in that.
Tor, okay.
Now, I want you to take your thumb, Tor, point it to me.
Yeah.
No. I mean, sorry. Tor, point it facing you.
Tor, face me?
And line up close one eye and line your thumb up with me. You did that. Okay, Tor, I did. Now you're a thumb head. Tor, okay, great. Now, switch eyes. Tor, hello. Camera 1, camera 2. Sure, what? So, what happened? Tor, well, my thumb moved out the way.
Yeah. Tor, your thumb jumped. Tor, yes.
Tor, okay, you can do that. So, right now I'm blocking the view of my left eye to that camera. I switch eyes. The thumb moved over, and now I can see the camera. Or exactly.
Tor, okay.
Your thumb moved.
Tor, right?
Tor, it moved, but it didn't really. It's still there in space. Your Tor point of view on your thumb changed. It was first at this angle, then it was at that angle. Tor, okay. So the angle that your thumb shifted you, we can measure that. Tor, okay. Tor, that's an angle.
Tor, that is an angle.
Tor, okay. Tor, right. Tor, so now watch. Do the same thing with me, except move your thumb much closer.
Tor, okay. Tor to you. Tor, to me.
Tor, mim.
Okay. Line me up. Okay.
Now switch eyes. So, well, yeah. Now my thumb's gone. Tor, your thumb goes way farther. Tor, yeah. I can barely see it. Tor, you can bar. So the closer your thumb is as you switch eyes, the bigger the angle. Tor, the bigger the angle, right? Tor, that is a precise geometric relationship between the angle that the thing moves towards and how far away it is. Tor, gotcha. Tor, provided you know the separation of your two eyes, right? Tor, okay. Those three things, separation of your eyes, the angle the thing shifts. There's an equation you put in those two numbers, out pops the distance. Tor, that sounds very cool. Tor, all right. And you see how that can vary depending on how far away the object is, how far away your thumb is. So, are you ready? Tor, go ahead. Tor, we do this with stars, Tor, in the galaxy. Tor, to find their distance. To find their distance. Tor, okay. Tor, but we don't have eyeballs to do it. We have Earth's orbit. Tor, so we're in one side of Earth's orbit. Let's call it. You take a picture of the sky in June.
Tor, all right.
You come around December, you take another picture. Some of the stars would have shifted. Tor, yes. Tor, now, the really far away stars, Tor, they're going to be in the same place. Tor, they're basically going to be in the same place. So this works for stars that are kind of nearby and intermediate distance. Tor, right? Tor, because you can see the shift in the position, Tor against the backdrop. Tor, and in your case, your thumb was the intermediate star and my head was the backdrop, right? Okay. And if you look carefully, my head would shift against that background. Tor, 1, 2, yeah. So, Tor, but it shifts much less. Tor, right, much less. Tor, much less. I'm farther away than your thumb is.
Yeah, Tor, I'm walking around like this now.
Tor, okay, Tor, so that phenomenon, that shift in your point of view is called parallax. Tor, right, okay. In order to get this sense of motion in a movie or in our space shows, if you're not going to use 3D glasses, you make sure there's sufficient parallax so that your brain knows exactly what's going on. So you have certain things that pass by faster than other things. Okay. And if they're not otherwise moving, but you're moving, the nearby things will move by much faster than the middle distance things than the far away things. That's why you're driving down the street. The trees along the side of the road go by way. The guardrail is in light speed. You go to the mountains, they're kind of there a while. Let's go to the moon. The moon just stays there. Chor, it's following you. Chor, that's it. Chor, why is it following you? Chor, that's why kids say, why does the moon follow me? Chor, because they don't understand parallax yet. Chor and I say, because the moon is not to be trusted. Don't let the moon man come get you. Chor, so why does the moon follow me? Because it is so far away. It exhibits basically no parallax for your movement. If you kept going in that same direction on Earth and off into space, then the moon would finally you eventually leave behind, Chort, right? Eventually, right? But so that's the answer to the age-old question of children. Why does the moon follow? Because of parallax, right? Okay. So let's get back to my people in this stupid-ass unit of measure. Are you ready? Okay. If a star is at a distance where half of the parallax angle is 1 arcsecond, its distance is 1 parallax second, 1 parsec. Was it portmanteau? Is that what they call that in English class? Portmanteau. So I don't know. So you take pieces of other words and make a new word.
Sure, yes.
Yeah. So you staple them together and you get parsec. Now ask me how far away that is. 326 light years and no star. Is that close? Sure, okay. The closest star is the Alpha Centauri system. That's correct. 4 light years away. So we have a measurement that's useless. No, because it measures nothing though, because there's nothing there. There's nothing there. The justification is that even though nothing is that close, 326 is kind of like 4 light years. The average distance among stars in a galaxy is measured in parallax 1 to 2 parsecs. The average distance between stars. So generally star people will still use parallax because it was 10 parsecs away. They'll still use it, but in all my classes I just converted it all to light years because 1 parsec versus 26 light years. A light year is completely easy to explain, right? And we understand that because light travels in the vacuum of space at a constant, at a constant. How far does it go in a year? And now we got it. And then you can actually take that out to as many as. Okay. And so that itself would cause mild confusion, but you get over it quickly because people would think a light year is a unit of time, right? But once it's explained, you never think that way. It's not time even though it says light years.
Okay.
So enter Star Wars.
The first movie.
And there's Han Solo bragging about the Millennium Falcon. The Millennium Falcon to Al Guinness playing Obi-Wan. Obi-Wan, okay. And Luke Skywalker is looking on hard this bucket of bolts. How are we ever going to get it and she busiket off belts? And where's my sister? 'Cause I want to kiss her.
Stop.
So he's bragging about his ship, and then Obi-Wan says, but is it a fast ship? Right? And then he gets flustered that it would even be questioned. So he says he did the castle run in less than 12 parsecs, right? Which, judging from what you just told me, is like saying I ran the marathon in 20 in the New York Marathon. I finished ET in a ER in Marcidias. No, it's worse than that. Well, go ahead. I finished the marathon in the 12:50. Right? Exactly. How tall are you? I'm 75 degree F. Pineapple's head. You're supposed to be air ATQ and K. His stuff you PQ OU a year. Escher, no mutual understanding of any measured quantity unless units comport.
Okay, that's ridiculous.
So now I don't know why I got so concerned by that line given everything else that's in the movie. Okay, why should I? But you know what? They're using one of our words, right? And they could have called me. I could have helped him out. It's just one more thing to add to how Star Wars does not give a F about science or objective reality. They do not care because it's fantasy and fine. You just pissed off 1 billion Star Wars fans out there. I am one of you people. I love Star Wars. Shoot. I read the books. Okay, that's how bad it is. Okay. But yeah, they don't give a crap about science. Yeah. So I feel guilty that the unit of measure exists at all. By the way, in Star Trek, they always used parallax correctly, even though light years would have been more interesting and fun. So this is the story of parallax. That is crazy. It's kind of with us to stay. But now tell me again what a parsec is. It's a unit of distance, which is torture, 1 parallel arc parallax or parallax arc second, arc second between what's on one side and what's on the other side. No half of that. It's 1/2 of this and 1/2 of this. So it's 1/2 of one side and 1/2 of the other together. That makes 1 parallax arc. Okay, I'll give you a Beathler chart arc second. Arcsecond. Tor, give me a B-fuss on that.
Okay.
Yes, because your elbows went a little too far, Tor. Okay. Tor, it is the distance at which half of the parallax angle to a star is 1 arcsec. Tor, there you go. The right Tor parsecond, Tor, right? And it has to be half because the two together make 1 parallax arcsecond. It's no, Tor, it doesn't have to be half. It's just by definition. It's half that angle is 1 arcsec. Or, oh, see, that makes less sense. Try. I know. I'm now to haras tartar and atomaka itemake sans Tor. I'm now to arrow defend it. I'm just here to explain it. And this is an explainer, isn't it? Sure. Yeah. But see, now I don't like Parallax. Sure, neither do I. Thank you. Let's shake on it. We're in agreement. All right, Tror Parsec. Sure, there it is. Everything you never wanted to know about a Parsec. Sure, and we got to go cuz a strawberry. Sure, until next time, this has been a Star Talk Explainer, as always. Thanks, Chuck. Your tour always a pleasure. Tour, keep looking up. When astronomers began trying to measure the universe, they ran into a problem that nobody on Earth had ever faced before. On Earth, measuring distance is simple. You can use a ruler, a measuring tape, or a GPS signal. Even if something is far away, like another city, we still have ways to measure it directly. But stars. Stars are unbelievably far away. So far that the normal tools of measurement simply don't work. You cannot stretch a ruler across space. You cannot send a measuring tape from Earth to another star. Even light itself takes years to travel between stars. So astronomers had to become creative. They realized that instead of measuring distance directly, they could measure angles. This is where parallax becomes incredibly powerful. Think again about the thumb experiment. When you hold your thumb out and switch between your left and right eye, the thumb appears to move. But it isn't actually moving. The change happens because your perspective changes. Each eye sees the thumb from a slightly different position. Your brain combines those two viewpoints to estimate how far away the thumb is. This is exactly how human depth perception works. Now imagine scaling that idea up to astronomical proportions. Instead of your two eyes, astronomers use two positions of Earth in its orbit around the Sun. In June, Earth is on one side of the Sun. 6 months later, in December, Earth is on the opposite side of the Sun. That means the baseline distance between those two observation points is about 300 million kilometers, the diameter of Earth's orbit. That's a gigantic baseline compared to the distance between your eyes. When astronomers take a picture of nearby stars in June and then take another picture in December, some stars appear to shift slightly relative to more distant background stars. That tiny shift is the stellar parallax, and we're talking about incredibly tiny angles here. Remember earlier we talked about degrees, minutes, and seconds of arc. A single degree is already a small angle. There are 360 degrees in a circle, but astronomers go even smaller. 1 degree contains 60 arc minutes. 1 arc minute contains 60 arc seconds. So 1 arcsecond is 1/3600 of a degree. That's incredibly tiny. To give you an idea of how small that is, an arcsecond is roughly the angle of a coin seen from about 4 kilometers away. Now imagine measuring something even smaller than that. That's the challenge astronomers face. When they observe nearby stars, the shift they see is usually less than 1 arcsecond. Sometimes it's just a fraction of an arcsecond. Yet from that tiny angle, astronomers can calculate enormous distances. Here's how. If a star shows a parallax shift of 1 arcsecond, that means its distance is exactly 1 parsec. That's the definition. And when you convert that distance into something more familiar, you get 1 parsec, about 26 light years. Now let's pause for a moment and appreciate how incredible that is. It means that by measuring an angle so small you could barely detect it with precision instruments, astronomers can determine distances across trillions of kilometers. That's geometry working at a cosmic scale. And once astronomers know the distance to stars, everything else becomes possible. Distance is the key that unlocks the universe. For example, if you know how bright a star appears from Earth and you know its distance, you can calculate its true luminosity, how much energy it actually produces. You can determine the size of stars, their temperature, and even their age. Distance measurements also help astronomers map the structure of our galaxy, the Milky Way. Without knowing distances, the sky would just look like a flat dome of stars. But once distances are measured, we see the three-dimensional structure of space. We begin to understand where stars are located relative to each other. We discover clusters of stars, spiral arms, and the vast structure of our galaxy. Parallax is actually the first step of something astronomers call the cosmic distance ladder. The cosmic distance ladder is a series of techniques used to measure larger and larger distances in the universe. It works like stepping stones. First, we measure nearby stars using parallax. Then we use those stars to calibrate other distance indicators like Cepheid variable stars. Cepheid stars pulse in brightness in a very predictable way. The rate at which they pulse tells astronomers how bright they truly are. By comparing their true brightness with how bright they appear from Earth, astronomers can determine their distance. Those Cepheids can then be used to measure distances to nearby galaxies. From there, astronomers move to even bigger tools like Type I supernovae, which act as cosmic standard candles. These supernova explosions are so bright they can be seen across billions of light years. By measuring them, astronomers can map distances across the observable universe. All of that starts with something incredibly simple, a tiny shift in a star's position caused by parallax. Now, modern technology has pushed this technique to extraordinary levels of precision. Space telescopes, like the Gaia spacecraft launched by the European Space Agency, are measuring stellar positions with unimaginable accuracy. Gaia can measure angles as small as micro-arcseconds, millionths of an arcsecond. That level of precision allows astronomers to map over 1 billion stars in our galaxy. For the first time in human history, we are building a detailed three-dimensional map of the Milky Way. Think about that. For thousands of years, humans looked up at the night sky and saw only points of light. Now we know where those stars are in space, how far away they are, and how they move through the galaxy. And all of it comes back to a simple geometric idea, parallax. But let's circle back to our controversial little unit, the parsec. Even though Neil Tyson jokes about being embarrassed by it, the parsec actually has one practical advantage. In astronomy equations, parsecs make calculations simpler. When astronomers measure parallax angles in arcseconds, the math works out neatly when distances are expressed in parsecs. That's why professionals still use it. However, when communicating with the public, light years are usually easier to understand. People intuitively grasp the idea that a light year is the distance light travels in a year. Since light travels about 300,000 kilometers per second, in 1 year it travels roughly 9.46 trillion kilometers. So when we say a star is 4 light years away, we mean that the light we see today left that star 4 years ago. You are literally seeing the past. Every time you look into space, you're looking backward in time. The farther away something is, the further back in time you see it. Look at the moon. You're seeing it 3 seconds in the past. Look at the sun. You're seeing it 8 minutes in the past. Look at the nearest stars. You're seeing them years in the past. Look at distant galaxies. You're seeing them millions or even billions of years ago. Space is a time machine. And parsecs, light years, and parallax are the tools that allow us to navigate that time machine. So while the word parsec might sound strange, and while Star Wars may have used it in a slightly questionable way, it still represents one of the most elegant pieces of geometry ever applied to the universe. From a tiny shift in a star's position, we unlock distances across the galaxy. From distances, we understand stars. From stars, we understand galaxies. And from galaxies, we begin to understand the entire cosmos. All because someone noticed that when you switch eyes, your thumb appears to move. That simple observation turned into one of the greatest measuring tools in the history of science. And that's the beauty of astronomy. The universe may be unimaginably vast, but sometimes the key to understanding it begins with something as small as the width between your eyes. So the next time you look up at the stars, remember those tiny points of light are not just decorations in the sky. They are distant suns separated by parsecs of space, their light traveling across the galaxy to reach your eyes. And with the tools of geometry, physics, and a little curiosity, humanity has learned how to measure that enormous cosmic ocean. And honestly, that might be even more impressive than making the Kessel run in less than 12 parsecs.